Hi, hello everyone. Welcome to this particular section of the webinar. Um, so we are on time for right now. It's Eastern time at 10 a.m. here. So I think I'll get started. Um, so today's main topic would be about OPC servers and safe operations. So OPC, I'm sure you guys who attend this meeting would know probably a lot of you will actually know much more than I do. I only did a few of the OPC projects, but today's main focus, I will actually try to see if there's anything that I can bridge the information gap between OPC servers and some of the safety standards out there. Because I do see that OPC has a lot of features within the whole framework and architecture that they can actually allow a lot of the implementations and alignment with these functional safety standards, alarm management standards, and also cybersecurity standards. So that's the main theme of today's discussion. Um, before I get started into the main part, because the way that this webinar is being organized, so if you have any question, feel free to type in to the software, the GoToMeeting software, and I will try to answer them at the end of the webinar. And hopefully I don't overrun it again this time, that I'll be able to answer some of the questions at the end, or else I will try to answer them one by one through emails. So you see my contact information at the end of the webinar. Feel free to write to me, and also feel free to type into the questions. I can get a compiled list of all the questions after today's session, and then I will try to answer them one by one. So a little bit about myself. I'm Paul Chen. I was actually working for Exida in the Asia Pacific office. I was based in Hong Kong, but I was working remotely for the Singaporean office. And later I was transferred here to the US a few years ago. I started out with a big, massive process safety, hazard seal selection workshop back in uh, South Korea. And it lasted for 3 months. I did a lot of Korean barbecues there. It was it was really nice time, and also that introduced me to Exida, and also I got into Exida ever since. After this massive workshop, I got involved in various different activities related to seal verifications, alarm management, and I'm also getting more and more involved with the cybersecurity sides of the business here right now. And as I mentioned, Exeter was actually founded back in 1999, and our main focus of business are functional safety, alarm management, and cybersecurity in relation to the automation part of this of the industry. And a little bit more about Exeter. So we have the main three core, the way that we help our customer is by, first of all, providing a very powerful tool like the Excellencia, where you have different kind of activities that you can all use Excellencia to help you with, like seal verification, hazard, seal selections, alarm management, and even for maintenance records. You can use Excellencia for that as well. And also we provide a lot of different consultancy services for lifecycle services. And on the top of that, we also do certifications for either process or for the whole hardware. And even we do certifications for personnel, for example, like the CFSE and CFSP. And we also do assessment per the standards in a way to help the operation of the whole plant to be up to what's required within the IEC standards. We have our own books as well, different reference books, and we also publish different industry data in terms of the, I'm sorry, someone is saying that I'm not seeing the screen. I think it's being shown correctly here. Let me quickly check. Yeah, I think it's being shown correctly here. So we also have publish our own industry data handbook, where we have different failure rate published in those different handbook, which we termed as SERH, for different part like the sensors, the PLCs, and also the final elements. And also we have a lot of reference books as shown here. And very importantly, we do a lot of our certifications, and certification can actually be very, very important in today's discussion, because we are looking at software. OPC server is a kind of software, and we do that kind of software certifications, and we are part of the global leader in terms of certification as well. We are the leader in the global in the certification when compared to other certifying agencies out there. We actually have larger product share in terms of the certifications globally when you look at all the safety device certifications, as is seen being here in the pie chart. And other than certifications for hardware, we also are global leader in terms of automation, cybersecurity certifications. In fact, we are partnered with ISA Secure in order for cybersecurity certification and cybersecurity's whole certification scheme. We partner with them to push out better cybersecurity certification, and we are one of the pioneer in terms of cybersecurity certification out there. And other than the certification, as I mentioned, we have our own tool. Why our tool is very, very powerful is because we have this mainly, first of all, everything started with silver in a way, because silverification is a very, very complicated mathematical calculations, and the proper way to do it is using Markov modeling. And we are one of the, I think actually the only tool out there, existing tool out there, that integrate an industrial database in terms of different failure rate of different make and models, and then that can calculate the whole PFD average or PFH based on those input data, and then using Markov modeling to do a very accurate mathematical deduction based on that. And that started out this tool as at a very, very good start. And then later on, we try to implement more and more into this tool, like PHA, LOPA, SIL select, and SRS information, SIL stat, and also SIL alarm, which is related to the alarm management part of the safety part of the operation. And because we have different modules linked together that's built within one big tool, it's also easier to let different information to flow. And as you might know, for example, information from cybersecurity, for example, which is actually required by the IEC 61511 standard to get into the part of the SRS in a way, because everything has to be, say, as in terms of security, it should be as assessed and looked at before you actually go into the design of the whole SIPs. And because of that, these kind of information can go through across different layers and different part of your management cycle, of your functional safety management cycle. So in a way that you can have a better intelligence data core that kind of facilitate the movement of different data, sometimes not just for the operation, but as a whole, it can also go up to the business side for better management and better data collections as well. So that's a little bit about Exida and what our strengths are at. So let's go into how everything started with OPCs. So everything started with a practical reason. It started with a lot of different SCADA systems and PLCs out there back in the 80s. And because they are of different brand and different make by different vendors like Siemens PLCs, Allen Bradley of Rockwell's PLCs, and also very primitive Modbus and also engineering stations, they can't really effectively communicate with each other. In the past, actually, the way they do it is that they need to have different software just to design specifically to bridge the information, for example, from a Siemens PLC to a Allen Bradley PLC. So they think that, so the OPC started in a way that, so we can bridge these kind of gap so that everyone can communicate with each other. OPC stands for, according to the standard, to the OPC standards, is the Open Platform Communications. It tries to standardize the different data exchange and the connectivity, and also very importantly, the interoperability for the operation of across different make and models, so that the whole protocol, the structure across different make and systems can be make and compact together into one framework. It is specifically for industrial automations. In terms of audio industrial automations, and also there is a specific client and server architecture over there. For example, the different PLCs and sensor valves, they send data to the OPC server. The way that we call it server is because it acts as a kind of a database, not exactly a database, but it gathers also all these informations so that the OPC client and other software application layer that can read or write from or to the OPC server. And the OPC client usually would be built into the like an HMI system or within the SCADA system or actually within the PLCs that they can show or represent this data information to the users in a way. And OPC was originally developed as an extension of Microsoft's framework back in the 90s. It specifically is for a kind of object linking and embedding for the process control. And because of that, so all the OPC, the objective of OPC tools has to be follow the OPC standard in a way that everything needs to be interconnected, in a way that everything, the interoperability and also intercommunication within different tools needs to be required and confined and also be stressed. And also there's also a very good framework of what kind of data are present within the server as well. And right now the most updated framework out there for OPC is the OPC UA framework. I would talk a little bit more about OPC UA in the last part of this webinar because it's kind of tightly related to how the security works within the OPC UA framework when you compare to the outdated framework, which is the OPC DA. And I would like to talk about how OPC framework, the whole framework, can actually be related to the different kinds of standards out there, like the alarm standards, ISA 18.2, the functional safety standards, the IEC 61508, or the cybersecurity standard, the IEC 6243. So in fact, different parts of the OPC standard are actually in relation to that particular part of the functional safety standard or alarm standards. So the OPC standards actually has strong reference to these kind of IEC standards as well. So let's first dig into the alarm part of the OPC standards. So for alarm management, we all know that alarm management is for better managing your alarm system. That's why in order to manage your alarm system, you need some kind of input, right? So already out there right now in the market, there are several tools actually developed by certain manufacturer that they try to help with the process using OPC technology. For example, the Delta V system, they actually have the Delta V OPC event server where they gather information about process alarms, status changes, operator changes, all these configurations or installations, all these information that's happening within the Delta V system. And if you need to bridge it to like another SCADA system using another PLCs, so they can actually allow this kind of information for flow into other system or when you try to look at it at a much higher level. And this would be very, very important because all these information listed here are KPIs, key performance indices of that particular alarm system. And these would be very valuable input for a review of your alarm system, which can be alarm rationalization. So these are very important information. Other than just bridging other two different make-in systems, within the OPC framework, they actually have a strict definition and they lay out laid out in details about extensively about what kind of information or alarm matrices needs to be shown within the OPC framework. They have a special event and filter function within the OPC framework that they try to filter out the alarm or some special events based on some special conditions. For example, when you see more than a few, you can set up filter out all the alarms. That's when you see more than 3 alarms coming up within a defined period of time. And they define all these matrices within the OPC Part 9 standard there. As you can see, these are the different matrix types within the OPC that's defined. A few of the very important information right here shown would be like the maximum active state. That is actually referring to the maximum time for the alarm to be at the active state. So if the alarm is active for a very, very long time, that means that there is something wrong with the alarm. Either that the operator doesn't do anything to help with the situation, or the alarm is basically just something that the operator can't do anything to actually clear out. There is also something like maximum re-alarm count that calculate the re-alarming of one particular alarm. If the alarm is re-alarming a lot, that means that there's something wrong with the alarm. Maybe it's a kind of a problem within the system that allows the alarm to come on and on again and again for a very long time. And these kind of matrices are very important because they are closely related to these alarm management issues, very common ones as well. For example, the alarm overflow, whenever there's too many alarms for the operators to actually cope with within a very short period of time. And there's alarm flood situations where you have a lot of alarm coming in. A lot of alarm coming in and you can't really deal with that many alarms coming in a way. I'm getting sorry, I just checked the question part. It seems that a lot of people can't really hear the my presentation. Is it a common issue? One suggestion is actually to go to the YouTube where they have connection and sound over there. because we're also doing broadcast at YouTube side. Yeah, it seems as for certain people, they also have no problem with the here with the sound and audio. Yes, yeah, a lot of people are actually feedbacking there's no problem with the audio. If you have any problem, maybe try to go to the YouTube site, the YouTube link that can actually help with it. Great, I think I will continue the presentation. Thank you for all the feedback. So another thing that's very important when it comes to alarm management issues is a problem with like the standing still alarm. As I mentioned, something that would be related to the matrix, that the maximum active site right there, that the alarm just stand there. There's nothing that you do. It can be there for several days or 7 weeks. I've seen alarms standing there for 2 whole years, and no one did anything about that. And there might be some chattering alarm that will be related to maybe the re-alarm rate, that within a short period of time, it gets alarmed and then comes off, alarms and then comes off, on and off for a very frequently, so that it's a kind of a nuisance to the operator. When realize that when you put yourself in the position of an operator, and you look at an HMI interface, you realize that there are a lot of problems within like chattering alarms or standing alarms in a way that you can't really manage your alarm effectively in that case. So that maybe in a way that you start to develop a kind of untrust towards the alarm system. And then when there's something that's really going to happen, something problematic that's really going to happen, then you ignore certain important alarms, then you might actually get into a very bad situation. In fact, that is a lot of the past incidents that actually led to, because of the poor alarm systems. Also, so that's why we need a good rationalization. So the rationalization would be a good way to actually review all these kind of problems. If you see these kind of problems, and these kind of problems would actually be reflected on all the alarm matrices. And in a case that you can use the rationalizations to relook at the priorities and alarm settings that you can help with the situations. And in the OPC standard, they actually has a strong reference towards the ISA 18.2 alarm management standard. So the ISA 18.2 is specifically about alarm management. In fact, within the OPC standard, they use a lot of the terms that actually defined within the ISA standard, and they align with that concept in the ISA 18.2 standard as well. So this is an overview of the whole life cycle of the ISA 18.2 standard. You start by setting up a scope and philosophies, how you're going to handle this alarm, the alarm system, and then you identify all those alarms within the system. Then you go into something that's very important called rationalizations. And during the rationalization activity, we will look at all the settings, the alarm limit, what are the actions of the operators for if they see this alarm, what are the consequences if he or she doesn't do anything, what are actually the causes for this particular alarm, and very importantly, the priority for this particular alarm. And within the OPC standard, they have a data called priority, and they also define it as a combination of the concept of severity and response time. So the priority isn't just about the urgency. It's also a combination of concept of the urgency and also the severity of the consequence that you're trying to deal with using this particular alarm. So in a way that by aligning that kind of concept with the ISA 18.2 standard, you can actually use the OPC software in a better way. And very importantly, as we are talking about KPIs. So as you can see within the life cycle, these KPIs or alarm matrices would be very important or kind of being extracted during the audit, either during the audit or during the monitoring or assessment process. So when these data, when they are extracted, they can actually pass into the information flow within life cycle. They can go into the management of change and then go back into all these different steps and then go back into the rationalization. So in a way that, as you can see, this is a loop going on here, a positive feedback loop that you try to improve your system by reviewing, and reviewing, that you can minimize all the problems that's within the alarm system. Of course, alarm rationalization, there are far more to it. If you guys are interested, you can check out our other webinars. I also did a few webinars on alarm management myself as well. You can consider joining our course for alarm management, specific to the ISA 18.2 standard. So now let's go into functional safety. So before I talk about the OPC part of functional safety, I need to give you guys a little bit more information about functional safety. Functional safety is about the SIS, SIF. And for an SIF, safety instrumented function, it needs to be, there's a sensor, a logic solver to relay the information from the sensor to actually bring particular action on the final elements. And this particular action or this SIF with this structure of, with this architecture of sensor, logic solver, and also final elements needs to be set up in a way to protect against a specific hazard. One SIF for one specific hazard, for one specific consequence. And one of the matrix or assessment we look at how the performance of a SIF is through to look at their random hardware failure, which is represented by the PFD average and also the PFH, which is basically talking about how often it's going to fail. It's a probability of failure on demand. And PFD average and PFH are basically based on how the demand will work for these SIFs. So I won't go into details because it's like a full 2-day course for in order to actually go through all of these informations. But if you guys are more interested, please really consider going into our FSE course. Actually, I'll be teaching one next week. It's very extensive information about this part, and this one is very complicated as well. So how exactly OPC is related into this functional safety then? So a lot of the time OPC, because OPC is a software, so the way that it interfaces with the SIS is when you have a SCADA system or other kind of system that needs to interface with one particular safety system. And sometimes safety systems, there can be multiple safety systems for different purposes within a plant, like you have a BPCS system, like you have a burner management system. Sorry, that was a mistake. Burner management system, and also you have a general SIS system. And then you might need something to actually bridge them in a way that for the communications. So there we have the concept of safe communication. It is actually defined within the IEC 61508 standard that there are two different kinds of safe communications. One is the white channel. That means that the communication channel needs to be compliant with the IEC 61508 to look at all the SIL level and all the requirements. And the other one would be the black channel, where only part of it needs to be compliant with the IEC 61508 standard. And the OPC handle it is using the black channel. So in the OPC, standard, they actually define that they specify as a very special safety communication layer. That is right here, the bridge between the application, the safety application software, and also the OPC UA layer, the general OPC UA layer. So it's kind of sandwiched in between. And only part of this safety UA, this layer needs to be compliant with the IEC 61008, right there, only part of it. And the other part of it would be like a black channel. So you don't really need to be, for that particular part, you don't really need to be compliant, to be kind of subject to the requirement of the IEC 61508 standard. And because of this, OPCs, within OPC standard, they allow up to a SIL4 capability for safety communications. However, in order to get to SIL4, it's not easy task. It's not really easy task because there's a concept of residual error rate and relation to SIL within the IEC 61508 standard. In fact, if you want a SIL4 application, you need to limit for the communication channel that the failure rate needs to be less than 10 to the power of -10 per hour. That is not an easy task to achieve. And other than that, for that particular channel, according to the IEC 61784, which is Industrial Communication Protocol for Functional Safety, they actually also recommend that for the safety communication channel, that it does not account for more than 1% of the whole PFD average of the whole safety function, right there. And it's not easy to do that. That means that if your safety function has really low PFD average, PFD or PFH, then you have even higher requirement in terms of the random failure rate, in terms of the random failure probability for the particular safety communications channel. And remember, part of this layer is actually subject to be fully certified by the IEC 61508. That means that it also needs to be looked at the systematic layer and also architecture layer in terms of how exactly the SIL level works. SIL level isn't just about random hardware failure. It also looks at systematic failure capability and also the architectural constraint. So in that case, then it's actually going to be subject fully to the requirement of the IEC 61508. That's why it's not easy task, as I mentioned. In fact, the way that the IEC 61508 standard suggests in terms of how we develop the whole software is to follow this particular V model. So to follow this V model, it lays out different levels of design from really just look at the requirement up to the point of coding, and then you try to review and test them based on different level of the design. So if you guys want to know more, welcome to join our course, because this is like a whole full day course on this, just for this part, full day course. And there are also different security requirements and also coding guidelines. For example, how your code needs to be architecturally structured. Like you have to have redundancy in terms of the coding structure in order to actually make the whole thing work. So that's a very, very small, brief talk about the functional safety part, how it's actually related to the OPC. Now let's go into the cybersecurity. So for cybersecurity for the OPC, in fact, the OPC UA has a very, very rigid network and also requirement of the security layer that is compliant with multiple actually multiple cybersecurity standards out there. So I was relatively spend less time on this part because it's just basically being laid out in terms of all the information and requirements that's within the OPC standard. So about cybersecurity, actually within the functional safety standard, IEC 61008, they actually require that to be performed. As you might know about the Dustnet attack, so basically it was a compromised PLC that tried to fake the nuclear centrifuge rate in a way that it can have some kind of that it centrifuge too fast, and then you have some kind of runaway reaction or fissions in terms of how the whole plant, nuclear extraction process or whole nuclear plant can actually blow up because of that. So the way how exactly it's being exploited is that so it created a kind of change within a PLC program. And also it makes the PLC program to fake the output of the I/O modules. So that the main design flaw in this part is that the PLC input process image was read and write rather than read only, so that it can actually be overwritten from the client side instead of just something that can only be controlled by the PLC in a way. So what happened was that there was contained of 5 different zero-day exploits, and then they stole the legit code, and then they do something with it, and then they reintroduce it back into the system. It was supposed to be only targeting Iran, but then afterwards, it kind of spread over from in Russia, and then in Europe, and then over the world. I believe the situation right now has been solved because it's been several years already, and you just need to fix the software bug or increase the security level within that. But as you can see, this is something that's going to be very problematic when you have something that can be read and write rather than just read only. And within the OPC network, within the OPC requirement, they actually has a very robust security layer requirement within the architecture, like authentication, some kind of security token, authorization, whether only certain personnel can access to it, a confidentiality in terms of the communication channel, whether there's any kind of a special secure channel for that and encryption for that, like the signing and encryption between different platforms, integrity, and also they have a robust objective to guard against DOS attack for the denial of servers, like overflooding the server in a way that you can't really do anything. Your service is being denied because it's overloaded in terms of the resources that can be utilized within the system, and availability and auditability. And because of these kind of setup within the OPC framework, you can right now actually use Modbus within the system, because Modbus does not have any security built in. It's a very primitive, easy way for communication. Like for a road to Rome, they don't really do any kind of check in the past, back in ancient Rome. So by layering a top layer onto the Modbus, you can actually integrate these kind of security layers and access controls like encryptions, authentications, and security tokens in order to introduce such kind of security into the Modbus situation. So that's a very brief idea of how cybersecurity works. But when we come to real world engineering, even though there's a robust framework for the OPC standard, but the way how we use it can usually result into problems. And this is actually something from my friends, because he was too sick of the microwave uh, range that's just suck all the smoke in and then blow it out at the top. So he made a kind of suction, like a suction range hood himself, and then suck all the smoke and lead it out of to one of the window of his. So this is real world engineering. This is what we care about, because mostly we care about how to make things work, but we don't think about how to make things secured and audited. Even though it's using dryer vent, I don't know whether it can actually withstand the kind of temperature that's within the range hood. So who knows? Maybe something bad might happen. So we don't know, because usually when it comes to real world engineering, we just care about how things work. So even though we have existing framework, but there are a lot of misuse of the OPC technology. And what I see, the problem is that a lot of the companies or operation out there, they do not really specify for a particular subscription rate. So for example, let's imagine for drilling application. For drilling application, you have, for example, you have a connected framework of a big SCADA system network to overlook a lot of different PLCs of either of the same brand or different make. And then they try to send data at a particular frequency, maybe per second. They send the data back to the OPC client from the OPC server. So they use OPC client, UA client to monitor everything. Is the subscription rate, refresh rate of the data actually reliable? I did a test on the subscription rate for Rockwell L7 controllers specifically last month. So there's interesting things. We tested about 4 different client and server combinations and realized that for one particular combinations, if the tags is about 4,000, that means 4,000 different tags of data entry that it needs to read, then the refresh rate is actually more than 28,000 milliseconds, which is close to 4.5 minutes. And the problem with this, especially in a machinery application, is that quite a number of machinery sieves, they are not really automatically initiated. They needs to be manually initiated. So in a way that if you lost 4.5 minutes, would that be enough to prevent or quick enough to prevent that particular hazard? So that's a lot of problems because of this. And actually, within the standard, they mention about setting up all the specifications, because all these information needs to be set up within the specifications. So when you try to design the whole system, everything can work accordingly. And maybe something wrong with the settings of this particular client and server combination. Maybe within the setting we can tweak it in a way that it can reduce the subscription, well, increase the frequency of the subscription rate, and maybe just not use this particular client server combination at all. Use another one if you need it to be more secured in terms of at a higher subscription rate. So that is one of the problems that I saw. The other problem that I see would be something like sharing the elements between the sieves and also the BPCS. So this is a problem not just to OPCs, because whenever you do that, you're not compliant with the IEC standard. And in a case, that is actually going to cause a lot of this problems, not just at the OPC side, but problems within the SIS system, problem within the BPCS system, and problem even for cybersecurity in aspect of that. So I keep hearing this, asking me, during the heads-up session that, oh, can I share the same sensor or can I share the same valve, which is even worse for a CIF and a BPCS system. So the way that they suggest is to connect the sensor to the BPCS system and also the SIF system and initiate this particular CIF from that particular sensor. And because the sensor is part of the BPCS system and they use a OPC server for that, so maybe within the larger server at the BPCS, and because the OPC architecture was designed only for the BPCS system, wasn't actually designed for this SIS system, so it's not really safety rated. So in a case that create problems. So you introduce one more path for the failure because you're right now actually can fail through the communication, screwing up the communication through the OPC network. And then you can compromise the integrity of that particular CIF because of this. And whenever we talk about independency, within the standard, they even strike for independency between different trips within the BPCS system. As you can see, within the IEC 61511 standard, that they try to separate all the hardware from one trip to another. From sensor, input card, CPU, output card, and also the final element. So they want to separate this to another trip at the hardware level already. So that's why you see whenever we talk about independency within the IEC standard, it's very, very demanding. So anything like sharing the same hardware between a CIF and a CDCS is basically frowned upon. It's not something that we need to and we want to do because of that. So another problem that we see is about using outdated software or framework in this case. So I talked about why we stress, for the whole presentation I stressed the use of OPC UA, the OPC unified architecture, rather than the OPC classic framework. So the OPC classic was actually an outdated OPC standard. Right now, everything they try to strive for is to transition to the OPC UA. So one of the reasons is because that OPC classic was actually developed by different modules independently in a way that they don't really comprehend with each other and connect with each other in a very secure and very good way. For example, they have in the past you have to have a different specific server for alarm events than the historian server. They are divided into different, as you can see, data access, alarm events, and historical data, and even data exchange. They have different protocols and different modules for that. So that complicates things. Whereas in the OPC UA structure, you have everything built within one big structure and framework. The other thing that's important is the OPC classic that it uses the DCOM. That the problem with this is that DCOM, first of all, is something that's quite old, and then it's only developed for Windows only because it's a Microsoft technology component. You can't really use it in other OS. And a lot of the operation system, they needs to be run on Linux. That means that you can't really use OPC on that. But the OPC UA is not really OS dependent in that sense. So that in a way that you can actually use it across different platforms. Another problem with the OPC Classic is that the OPC Classic has a big problem with firewall. It's very firewall unfriendly because in order for the OPC connection to work, you need to put a big hole in a firewall. It's compelled to actually free port from port 1024 to 65535. That's basically like opening every port within a system in order for the server communication to work in the OPC Classic. So in the past, how they did it to add extra, to add at least some kind of degree of security is that they need an extra layer of application to actually embed on the top of this particular firewall, maybe an extra layer of firewall to further limit the port in order to be ported. So that actually create a lot of problems because the interface between that particular layer and the firewall can also create problem as well. And also firewall upon firewall might have problems in terms of communications. So that's why it creates arrays of problems if you want to do it for security reasons. The other thing that's being constantly brought up by all the developers for OPC Classics is that they complain about how complex DCOM is. DCOM is complex and difficult to understand, and it's something that feels like it's developed as time goes. It doesn't really have a really systematic way of how everything works in terms of the technology. So it's more like real world engineering situation where you just wing it as the real world situation evolve. So in that case, it introduced a lot of bugs into the system. And because the OPC UA doesn't really use that DCOM situation, so in that case, then it's not. In that case, it doesn't really have that kind of problem with the bugs that's related to the DCOM. That's why always we need to push for OPC UA because of that. And also OPC UA has all these information and requirement on functional safety, alarm management, and also for the cybersecurity like security control and security layers. That's why we need to use OPC UA to use the most updated version of the OPC in order to have a better and safe operations. So that's about all about my presentations. So I do see a few questions that's being brought within the question tab. So I try to answer them one by one. So the first one I see is that can we actually take credit for an alarm as an IPL when the alarm from a UCP which is communicated through the OPC to the BPCS? So that's a very, very interesting question. So the only thing that's going to limit you from not taking an alarm as an IPL is that when the alarm is not independent from the initiating cause. So we need to make sure that the initiating cause is not really related to that particular alarm. For example, if that alarm is initiated from one particular controller, then that controller fails, then you can't really take that alarm as that particular IPL for that particular event. So if it's being used through the OPC, in terms of the how the connection works, if it's not, as long as it's not really from the same initiating cause, I don't see there's any problem for not taking it as an IPL in that case. So considering there is another question, which is, can we take a credit for a CIF as an IPL for another CIF? If everything is independent, let me see, except that the logic solver is common. So first of all, there's two parts I need to answer for this question. So the logic solver is common. It's not really too much of a problem when it comes to using CIF, because the PLC, they have within their architecture, within their control, within their software level, they have really rigid control in terms of independencies. So that's why everything is being, for each channel, is being treated as independent of each other, as long as it's actually built in within them. But for most of the SIL rated ones out there, they have such kind of independence and separations. So that's why we can actually do them when even there is using the same common PLCs in that sense. So the other part of this question is that can we actually take a SIV as an IPL for another SIV? So this is something that for example, this is something that actually how to put this, within our consultancy expertise, that different approach towards this. For me, as long as the math works, it's fine. Because you need to make sure that, for example, for a SIV, for example, there are two SIV. One SIV is potentially being built as a SIL1 application. The other SIV, you don't know yet, and then you have maybe right now you're aiming at SIL2, but you want to look at the burden of that particular SIV, right? The SIL target on that particular SIV. So let's call that SIV2. For SIV1, if you set it up as a way that it's going to be SIL1, so you need it as a RF of about 10. So you need to put that into your SIL selection calculation when that happens. So in that case, that when you doing the calculation and incorporate other IPLs into it, and then you arrive at the target SIL for that particular SIL, SIV, the SIV2. So in that case, you can use it as such, especially when everything is independent. The sensor, file elements, and also the IO cards right over there. So because of that particular structure, how it works. We also have a lot more questions popping up. So there's a question about can we use the same valve for BPCS and CIS? Sonar valve connected to the CIS while the valve positioner is connected to the BPCS. The solenoid valve is SIL2 rated. The valve is normal control valve, not SDV. So as I mentioned, this is definitely no. And especially when you say that it's normal control valves failure rate, even for, how to put this, for a lot of the SIVs, the main thing that's going to drive up the failure rate is about the valve body. And a normal control valve is not really applicable in a safe situation, in a safety valve application situation. A safety valve not just needs to have very, very low failure rate, but also a safety valve needs to be inspected in terms of their in terms of their proof testing, how they're going to proof test it, and also how the manufacturer process that's going in to minimize the systematic error and also the architectural error as well. So in that case, it's never ever being compliant with the IEC standard that you can use a normal control valve as an SDV, as a safety valve like that. In fact, a lot of the normal control valve has a big problem with sticking. It sticks because it's a normal control valve. It keeps moving in a way that it's being used a lot, and it has a lot higher failure rate than those safety valves because of that, because of the constant moving of it. And in a way that it also might have some kind of premature failure because of the constant use of these kind of valve. And imagine a lot of the mission time that being used within a sieve. We consider 10 years, 15 years, up to 20 years. But normally a control valve like that needs to be overhauled maybe 3 years or 5 years. So in that case, that is another reason why you should never use a normal control valve like that in a safe application. So I do see a lot other questions popping up, but we are a little bit out of time right now. So I would answer them one by one afterwards. If you have any more questions that you want to bring out, feel free to send me a question through my email right there. And you guys can also go to our Twitter, our Facebook, and LinkedIn. We keep publishing new information like new courses or new webinars or new white papers or new information out there for just for the betterment of this safe operations across the industries. You can also try to consider maybe look at some of our books for reading. Those are very important and very useful for better operations and safe operations as well. So I'm really grateful that you guys come to this webinar. This particular webinar is going to be uploaded on YouTube later, and we will actually send out the link later. And you can actually look it up in our YouTube channel as well. Probably maybe 1 week from now, it's going to be up there as well. So really grateful that you guys join me at this particular webinar. This webinar might not be live sometimes in the future, but so therefore always type in your question or maybe write to me for all those questions. I'll try to answer them one by one myself personally. Thank you very much, and have a nice day, and also take care in this COVID situation. I hope everything is going to be fine and safe. Thank you very much.